All right, let's take a look at today's lesson. So we're going to do a couple of different things. We're going to do a continuation on the fundamental theorem, and then we have another exciting part where we're looking at scary Riemann sums. So let's start with the fundamental theorem continuation. So we have a position value that they've given us. We don't know why yet, it's okay. We're told that the first derivative is continuous. We have this value, which is an integral of the first derivative. We're told is 20. Okay, so they want us to find f of 8. Okay, when we first look at that, we're like, what? So how can we use fundamental theorem? Why don't we take this integral and let's just do our, write it as a fundamental theorem. So like the f of b minus f of a. So let's do that. So we have the integral from 3 to 8 of f prime of x would be, that would be f of 8 minus f of 3. So that's using our fundamental theorem. And this is what we're interested in. We want to solve for that. Okay, we could do that. So let's see, what information do we have? We actually can, we know the value of this. The value of this is actually 20. So I'm going to replace that with 20. We don't know f of 8, that's what we're looking for. F of 3, we do know f of 3, we know the value of f of 3 is actually 5. So now it's just a matter of solving for f of 8. And so I would add 5 over and get 25. So that's a very abstract look at using the fundamental theorem. Okay, just kind of pulling that all apart. Let's look at our next one, another abstract one. They give us this, it's kind of, wow, it's a lot going on there. And they want us to find just this part. Well, that part is kind of embedded inside there, isn't it? I mean, it's right in here. So what are we going to do? Let's go ahead and use, we don't have that many integral rules that allow us to break things up, but we do have this one. So let's go ahead and break this apart. So I'd bring the 3 out, negative 1 to 4 of f of x dx plus the integral negative 1 to 4 of 2 dx, and that all equals 28. Okay, that's a good first step. Let's kind of focus on what we want to know. So what we want to know is this part right here. This is the little piece right here that we want to solve for. Okay, we can do that. So let's see. So I don't know what that is. So we've got 3 times, okay, that's what we want to know, plus. So this integral right here, if you remember when we first started working with them, well, we can do fundamental theorem or otherwise. So if we think about the graph, that would be at a y equals 2. We'd go from negative 1 to 4. So we're just thinking about, this would just be a rectangle. Remember when we did that? And this width would be 5 and this height would be 2. So this integral would just be 10. We can do it that way, or we could do fundamental theorem. Really, it doesn't matter. Okay, so we're making some progress. Very good. So I need to solve for that integral. So I would move the 10 over. Okay, so it's 28 minus 10 would be what, 18, and then divide by 3. So 18 divided by 3 would be what, 6, and so that would be our answer. So another example that's pretty abstract on fundamental theorem. All right, one more. We're going to do fundamental theorem looking at a piecewise function. And notice that we want from negative 1 to 4, and that spans both pieces. So we're going to have to actually split this integral in two because of the way the piecewise function is written. All right, so let's start with the negative 1. So we go negative 1 to 2 of this top piece, because that's when x is smaller. So it would be 3x minus 1 dx. Plus, and now we're going to go from 2 to 4 of this other piece, this lower piece, x squared plus 1 dx. So that's our first task, is to basically break them apart because it's a piecewise, and the part that we want to integrate overlaps both pieces. So now we're just going to do just two regular old integrals. We're going to do the reversal power rule. So the antiderivative of 3x would be 3/2 x squared. The antiderivative of -1 would be negative x. And we would evaluate that from -1 to 2. Okay, so let's look at the next one. So the antiderivative of x squared would be 1/3 x cubed. So remember the reversal power rule where we add 1 to the exponent and then divide by that. So 1 plus 2 is 3, and dividing by 3. Just a little reminder. And the antiderivative of 1 would be x. And we want to evaluate that from 2 to 4. Okay, looking good. So now we do our f of b minus f of a. So I've got 2/3, oops, it's 3/2. 3/2, and then I've got 2 squared minus 2. Okay, now I'll put the -1 in. 3/2 times -1 squared minus 1 plus. Okay, so then we go to our next little piece. So I've got 1/3 4 cubed plus 4 minus. Then I've got 1/3 2 cubed plus 2. And that is a lot of arithmetic. It's a lot. I will just tell you, when you finish with all the arithmetic, and it's a lot, you should get 133/6 after all of our arithmetic. Okay? All right, so now we get to come to our very interesting concept. Okay, so yes, I made it up. They're really not called scary Riemann sums. I just made that up because we have regular Riemann sums, which you all know it's like adding up rectangles, pretty easy. These are also a form of Riemann sums, and let me explain the difference. So we don't want to get them confused. So this kind is really the definition of an integral. So I want you to take your mind back to, remember way, back in the day, the definition of a derivative. Remember that? The limit as h goes to 0 of f of x plus h minus f of x over h. Remember that? Yes? And remember how we learned this first, and then we learned all the derivative rules, and so we didn't have to do the definition anymore? Okay, so this is the definition of an integral. And look, it's got a limit, and it's got something extra fun. It's got a summation. Wow. Now, I will tell you and comfort you and let you know that we're not going to have to calculate an integral using the definition of an integral. We are not going to have to do that. So, yay. What we are going to have to do is be able to go back and forth. I need to be able to go from this form to this form, and I also need to be able to go from this form to this form. I just need to be able to go back and forth, and that's what I'm going to teach you how to do. We're just going to learn how to go back and forth. That's all you will be expected to do, okay? Just go back and forth. So let's do that. We're going to do one of each. We're going to go from this integral to the, this definition, limit of the summation, and then we're going to do the other one. We're going to do from the limit of the summation to the integral. So I'm just going to show you how to go right back and forth. Okay, good. So these are the formulas that we will need. If they don't tell us which type, which endpoint, we'll just say, this is the one, this is the easiest one right here. This is the right endpoint. And this, is what we would use if they didn't say. Now, I think the next example is using a left endpoint. The only difference between these two, if you'll look, is how this I is set up. In the right endpoint, it's just the I, and the left endpoint, it's the I minus 1. And I'm actually going to use the letter K for the I, instead of like the I, because this notation over here is using a K. That's why. I'm going to use a K instead of an I, and that's okay. You can do that. All right, so I want you to also notice that this delta x appears in these as well. So it appears in both the right left endpoint and delta x, what delta x is. Okay, so I'm going to pause there for a second. One other thing I want to make note of is that this is actually x. We're going to replace this right here with all the x's in our equations. That's how it works. Okay. All right, so let's jump into the first one. So this number, if you recall, this number is A and this number is B. Okay, that's what those are. Those are A and B. So the first thing that I would like to do is calculate delta x. So I'm going to use this formula right here. That formula, delta x is B, which is 6, in this case, minus A, which is 2, over n. Okay, great. We'll simplify it, and we get 4 over n. So that's what our delta x is. It's 4 over n. Okay, great. Making progress. All right, so let's start writing. So this is the regular integral. We're going to use its definition. Let's start writing this kind of weird thing. So they all start with limit as n goes to infinity. That's just how they look. Then you've got the summation sign, and they're using k. You could use, I if you want, but they're using k. This part is going to be the same no matter which one you do, right? That's the same. So what is this piece right here? This is the function. This is the function, and this is delta x. Okay, that's the function, that's delta x. So we already know what delta x is. Let's just go ahead and write it here. 4 over n. Okay, that's what delta x is. 4 over n. Check, I've got the delta x part taken care of. The harder part is the function part. So this is the function right here, right? X squared minus 3. So what I need to do is I'm going to take this x right here, this a plus I delta x right here, and I'm going to put it exactly in place of this x right there. That's where it's going to go. So okay, so remember a is this number right here, 2. So 2 plus, and instead of an I, I'm going to use a k. Okay, and delta x we already calculated, which was 4 over n. And this part right here goes in place of the x, so it's going to be squared, right? This would be x right here. So I'm just going to underline that. So this part right here is x, which is this part right here is x. And then I've got my minus 3. And that's that's it. That's what I do. I just basically went from an integral, regular looking integral, to its definition. Okay. So now let's go the other way. Let's go the other way. So what do we want to do? We want to, this is, this part right here, we know that looks all the same. We don't need to worry about that. What do we think this is? Okay, yeah, that's delta x, right? That's what that is, delta x. So what do we think this is? According to our formula over here. Yep, that's a. And this part right here is k times delta x, right? So here's the k. That's right there. And we know, we just actually looked at it. This is delta x right here, right? That's what that is. Delta x is that. Okay, so I hope we've identified the pieces that we need. So we know a. So where are we going? We're going right here. We want it to look like this. So what do I need to find? I know what a is. It tells me right here it's 4. I need to find b. Okay, and I need to figure out what the function is. All right, we got this. So let's do it. So I've got my integral. A is 4. Got that. So let's write our delta x out. Delta x is, b minus a over n. All right, so we know what delta x is, right? It was 6 over n equals b minus a is 4 over n. Now my job is going to be to solve for b. So those n's cancel out, and I have 6 equals b minus 4, or b is 10. So if b is 10, that's what goes here. Okay, great. We've got like half of our job done. We know what the bounds are. The last thing we need to do is to write the function. Now, if you'll recall, this part right here goes in for the x, right? This a plus I delta x. So a plus k delta x. This part goes in place of the x. So x, and then what's happening to this x? This x is squared. And that is, that's it. That's our integral. Okay. All right, so we have one more example to do, and actually it's a free response. It's got one of these in it and a regular Riemann sum. Oh, yay! We'll get to be able to compare those two. That sounds fun. Okay, so here we go. So we have, let's look what we got going on here. We've got the height of water in a storage tank during a 15-hour period is given by a twice differentiable function. Do you remember what this means? This just means you can take two derivatives. That's all that means. You can take two derivatives of it. H is measured in feet. Okay, so H is measured in feet, and T is measured in hours. All right. The graph of H is concave up. I don't know why they're telling us that, but we might need it. Concave up on this interval. Okay, so that's probably important, so I'm going to make note of it. And selected values of the derivative of h prime are given in this table. So we've got a table over here that has h prime in it. At time 2, the height of the water is 7 feet. So here they're giving us a function value. We'll probably need that for something, so let's make note of it. At time 2, the height is 7. All right, so the first part is asking us to use a tangent line approximation for h at the time t equals 2 to estimate h of 28, the height of the water, at time t equals 2.8. And then say whether this approximation is an over or an underestimate. Okay, we can do that. So a tangent line, let's just write, so we need our tangent line. So y minus, and we want, we've got our t value of 2. Do we know what our h value is at 2? Yeah, they happen to give it to us in the prompt, right? The h value at 2 is 7. Okay, we need to figure out our slope. Okay, so our slope, we need h prime of 2. We need h prime of 2. Where are we going to get that? Okay, well, if we look over here in our table, we do have h prime of 2. H prime of 2 is 0.3. So now that is our tangent line. Okay, so we use our tangent line to approximate h of 2.8. So what does that mean? That means we're going to put the 2.8 in where the t is. So y equals, I'll just move the 7 over, plus 0.3, and then we'd have 2.8 minus 2, which would give us 7 plus 0.3 times, let's see, what would that be? And this is non-calculator, 0.8. And we know 3 times 8 is 24, right? We've got 2 decimal places. So y is going to be, or we can just say h of 2.8 is approximately 0.3 times 0.8 would be 0.24. So 7 plus 0.24. And that would be in feet. Okay, so we've taken care of the first thing they've asked. There's our approximation. Then they want to know, is this an over or underestimate? So it's a tangent line. If you recall from back in the day, right, when we were doing like concavity, so this is concave up. If I have a tangent line right here, would this tangent line be an over or underestimate if it's concave up? Well, if I am trying to compare, this point to this point, this tangent line is going to give me an underestimate, right? So concave up would give me an underestimate. So do we know whether this function is concave up or concave down? Yes, we do. It was written right up here. It's concave up, so therefore, we're going to say since h is concave up on, and we'll say the interval because they love that. Okay, the tangent line lies under the graph. So the approximation is an underestimate. Yay. Okay. Okay, great. Let's take a look at part B. Ooh, use a right Riemann sum. Okay, now we don't want to get confused here. It's telling us to use a right Riemann sum. It's not telling us to do a scary Riemann sum. Nope, just this regular right Riemann sum with 5 subintervals indicated by the data in the table. So let's look at the table. We want to go from 2 to 14. Well, okay, well the data is from 2 to 14. So, you know, I'm not that good with, I need to write it out. Okay, so I'm just going to write it out. Like I've got a 2 here. We'll just put it over here, it'll be easier. So we started at 2 and then 4, then 5, 8, 10, 14. Okay, so I've got 1, 2, 3, 4, 5. I've got 5 little rectangles, right? Okay, so I could kind of think through that. You know, I've got like little rectangles. And of course, I'm making this up. I don't have any idea. So these are my rectangles. So I would need the width of each rectangle, right? That would be 2, and that would be 1. My width, let's see, that would be what, 3, 2. They're all different, and that's okay. Those would be my widths. And I need my heights. Now it tells me to do a right Riemann sum, a right Riemann sum. So I need to use the right sides of each of the little rectangles. So I would use this side for the first rectangle and this side for the second one. I'm using the right sides. This one for the third, this one for the fourth, and this one for the fifth. I mean, that's what I would do. That's how I'm going to write up my Riemann sum. And if you recall, I have to write those numbers. I need the products and the sums. So let's do that. So our integral from 2 to 14 of h prime of t would be approximately, all right, so my first width was 0.2, and then I read off the table, you know, I'm reading h of 4, kind of because I want the right side, so right would be 0.6 plus my next width was 1. Okay, I guess it'd be easy to just leave it like this. My next width was 1, and I would need 5, this one, so that would be 0.7. My next width was 3, and that height would be the 8 one, which would be 1.4. And this height would be what? 3, 2 between here. And I need the height at 10, which would be 2.3. And then my last one's width would be, what, 4 times, and the height would be 7.7. Now, if this were a problem on the AP test and you didn't have a calculator, you could totally go like this. These are all numbers, so it would be legitimate. You could say that it's, I mean, I guess I can rewrite it, or yeah, let's just, you don't actually have to do all of this calculations. In fact, it would probably be better if you didn't by hand. Now, if you have a calculator, that's a different matter. I mean, you still could leave it like this. But I need to write my units, and that's in feet. Now, if you really, really, really wanted to multiply and add all that together, you should get 41.5 feet. Okay, so either of those answers is fine. This could be one answer. I could write it like that. I could totally write it like that, but I need the units. Or I could go ahead and, you know, add them all up and multiply and get that. All right, so let's take a look at our next one. Is the approximation in part B an overestimate or an underestimate for that integral? Give a reason for your answer. We know about the concavity. And so let's think about this. We did right Riemann sums, and we're concave up. So since H is concave up, we need to think about the definition of concavity. In the definition of concavity, it tells us that the function is concave up if the first derivative, h prime, is increasing. It's increasing on 2 to 15. Okay, so let's think about that for a second. So if we have an increasing function and we're doing, right Riemann sums. So my right part, right, remember those right Riemann sums, the right part is the y value, then we would have an overestimate. Since it's increasing and right Riemann sum the approximation is an overestimate. I just want to make sure we understand that your reason can't say like, oh, the rectangles are bigger, they're outside. They can't say that. That's not okay. The explanation has to be like this. So we've got to talk about, concavity or the function increasing or decreasing. This h is the function, is increasing. Since it's increasing and a right Riemann sum, that's why it's an overestimate, not really because of the boxes. That's just to help us, visually understand. All right, last one. Oh, yay, we get to do the crazy Riemann sums, the scary Riemann sums. This is a regular Riemann sum. This is a scary Riemann sum. I hope you can see the difference. Regular, like regular, and scary. Why? Because it looks really weird, right? Look, we got our summation going on here. And it's a left Riemann sum. Oh, they're going crazy with us here. The left, we could see by this part right here, this means left. That -1 business, if you remember, if we look up here, see the -1 business up here for the left. That's why, and they tell us it's a left. Okay. So what do we need to do? We need to figure out how to write the integral. Okay. So because of our formula, we know that this part right here is delta x. Right? That's delta x. And I know that this is delta x times the k. But I don't have like a plus. Remember? I don't have like an a plus in here, which means a would be 0. That's what that means. A is 0. Because if let's just look at how these look. Right, so on this one right here, notice how I had the A was 4. I'm adding to this delta xk business right here, right? But on the one we have over here, I'm not adding anything to this. So that means A is 0. And we know that delta x is b minus a over n. We know delta x is 15 over n, we've got it right there, equals b minus a is 0 over n. All right, so those n's, they go away. So b minus 0 is 15, so that means b is 15. Okay, making progress, so I've got my integral from 0 to 15, yay. The last thing I need to figure out is what is, what does the equation look like? And actually, we don't have an equation. We've got this part right here. This part is for the x. That's where the x goes. Right? That part is an x. And that part is a delta x. And that's the function h prime. So really, it's h prime. And instead, they're not using x's in this example. They're using t's. H prime of t. And that would be our answer.